What up, math magicians? So today we're going to be looking at adding and subtracting radicals and rationalizing denominators. So as an example, assume we wanted to add these two values together, right? 5 square root of 2 plus 3 square root of 2. How do we do it? Well, think about 2 times 4 plus 3 times 4. How did we explain this via addition? Remember that 2 times 4 just means take the number 4 and add it to itself 2 times, right? So we have 4 plus 4. And then 3 times 4 means take the 4 and add it to itself 3 times. Right? And you can see here that since everything is addition, we can kind of get rid of the parentheses. And how many 4s do we have added together? Well, we have 5 of them. So this becomes 5 times 4. Okay, which if you want to simplify it is 20, but that's really not what we're looking at. So essentially, the way you can treat radicals is kind of like how you add variables. 5x plus 2x, right? This is 5x's, this is 2x's. You add them together, you get 7x's. And adding radicals is the same way. So if you wanted to think about this, how we explain that one, it's 5 square roots of 2. So square root of 2 plus 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 3 square roots of 2, square root of 2 plus square root of 2 plus square root of 2. So we can drop the parentheses, and how many square roots of 2 do we have? Well, we have 8, right? 8 square roots of 2. So just as we add variables, you can add radicals. And subtraction works the same way, so there's not really anything different about it. So for instance, 5 square root of 2 minus 3 square root of 2, right? We have 5 of them. We're taking away 3 of them. So we're going to be left with 2 square roots of 2. So typically we don't write, just like we don't write 2x as 2 times x. We could if we wanted to, but we kind of know what we're talking about when we just write 2x. It's the same thing with radicals. 5 root 2 means 5 times square root of 2. Okay, so what's a special case of this? Well, what if we have something like 5 root 12 plus 2 root 3? Okay, these radicals aren't the same, so we can't necessarily add them. But maybe there's a way that we can make them look the same. Now, how would we do that? Well, this is a prime number, so it's already a simplest form. We're not going to really be able to change this radical, but maybe we should look at the square root of 12. Okay. And from the previous section of reducing radicals, we know, or we can take this 12 and prime factorize it, right? And say this is 4 times 3. And we know 4 is a perfect square, so we can rewrite this as 4 times 3, right? And we have the product rule of radicals that we saw last section. The square root of AB is equal to the square root of A times the square root of B. So with the 12, it would be the square root of 12. We could rewrite it as the square root of, let me just do this one more time. Give myself a little bit more space. The square root of 12, this is the same as the square root of 4 times 3. And now applying this product rule of quotients, product rule of radicals, and so this will become the square root of 4 times the square root of 3. Like we said, this one we can't simplify, but we know what the square root of 4 is, right? It's 2. And so now you see that we've written the square root of 12, and it also has a radical 3. So square root of 12 is, we can replace it with 2 square root of 3. So let's do that. And so now we have 5 times the 2 root 3. Well, we can just multiply the 5 to the 2, and we get 10 square root 3. Plus 2 square root 3, we're just bringing this guy down. We have 10 root 3, and then we have 2 of them here. So how many total do we have? We have 12 root 3. Okay, cool. Alright, so now let's look at rationalizing denominators. Okay, so assume we have a problem that looks like this. 5 over root 2. So remember when you first learned fractions, your teacher would tell you something like We don't like it when the number on top is bigger than the number on bottom. We want this written as a mixed number. So you would do long division. 7 goes into 10 one time. 7 times 1 is 7. Subtract 3, and 7 doesn't go into 3, so you'd be 3 over 7, right? So you would write 10 over 7 as 1. You write it as 1 and 3 sevens. Okay, so this is kind of the same idea. We don't like, and I'm doing finger quotes even though you can't see it, we don't like radicals in the bottom, so we need to be able to get it out. Now, we have two different ideas. We know that if we have a number squared inside of a radical, right? Radicals and square roots essentially undo each other. So why is that the case? So let me change the number from 2 to, like, let's say 3. Remember that we have 3 squared, right? And the radical is just a fractional exponent. We said if we had the square root of a, this is the same as a to the 1/2 power. So we can rewrite this as 3 squared to the 1/2 power. And then from our product rule of exponents, we know that we can multiply the two powers. And so that looks like x to the a to the b power is equal to x to the a times b. Right, so here we have 3 squared to the 1/2 power. And so we would have 3 to the 2 times 1/2. Right, 2 is the same as 2 over 1. The 2's here cancel, and we just end up with 3 to the first power, which is equal to 3. Right? So we know that. So why don't we try squaring the top and bottom, for instance? Well, if we do that, right, we know that we're going to get rid of the square root of 2. We're just going to get 2 on the bottom. And then we get 25 here. But why doesn't this work? What are we doing incorrectly here? Well, what we're doing is, remember what the squaring means. We've taken the top, right? We've taken the top of our fraction. And what did we multiply the top by? Okay, 5. What did we multiply the bottom by? Square root of 2. So is this fraction equal to 1? No, it's not, right? And so the only thing that we could do here is if we did multiply by this, we'd need to multiply to the other side by it, right? But when we have a fraction like this with a root in the bottom, a radical in the bottom, there is no other side to multiply by. So you cannot use the square property here, okay? You can only do this when you have an equal sign. And since we don't, we're not able to do that, but we still want to get rid of the radical. And so what's the correct procedure? Well, it's we know if we can get this thing, if we can get 2 of them down here, the 2 squared inside the root, it'll cancel and we'll just get a regular 2 on the bottom. And so we can get that by just multiplying by square root of 2 on the bottom. Okay? And so now 5 times root 2 on the top is just 5 root 2. But then on the bottom, we have root 2 times root 2, right? And if we have 2 of them, we can write it as squared. And remember, roots and square roots and squares undo each other. And so essentially, the root drops off and we get 2. So we have 5 root 2 over 2. Okay? So just as another quick example, if we had this, what would we do? Well, we just want another one of these because the square of a square root is just the number itself. So we'd multiply the top and bottom by root 3. This is going to give us 7 root 3 on top. This will give us root 3 times root 3, which is equal to 3 times 3 is 9, right? 7 root 3. The square root of 9 is 3, and it's the same procedure, just using a different method this time. Now we're looking at it as the number on the inside times the number on the inside, and you can see that regardless of which way you think of it, as square of a square root is just the number on the inside, or you actually go through with all the calculation, you're going to get that number inside on the bottom, except without the radical there. Okay, and then so what if, though, we had something like this, where now we have what we call a binomial on the bottom. Binomial. What does bi mean? It means 2. Nomial means terms. So nomial here means terms. So bi, 2, nomial. So we have 2 terms on the bottom. Now, if we tried to employ the same strategy here, by just multiplying by the radical that we see on the bottom to the top and bottom, what happens? Well, if we take the square root of 3 and multiply it times the 2, well, we get 2 square root 3. And then we multiply the root 3 times this one, right? The radical drops off, and this is what we get. But notice how we still have a radical here, right? So we got rid of one, but then we just created another one. And if we keep doing this over and over, the radical is just going to shift from being over here to over here, right? It's just going to keep bouncing around. So this strategy, unfortunately, doesn't work here. It's not as simple as just multiplying by the radical that you see on the bottom. So what are we going to do? Well, we're going to use something called the conjugate, and I'll spell that out here for you. And this is a very important idea that comes back over and over, all the way up through at least calculus 2. And so what is the conjugate? Well, so if you have a term a plus b, the conjugate of the term is just a minus b. So, and likewise, if you have the term a minus b, the conjugate is just a plus b. So really the conjugate is the same first term, the same second term, but just change the sign in the middle. So since we have 2 plus square root of 3, here the conjugate is 2 minus square root of 3. And so we're going to multiply that on the bottom and the top. Okay, and so what are we going to get here? Well, remember your FOIL operation. You have to make sure everything in the first set touches everything in the second. And so 2 times 2, right, that gives us, so let me do it here so it's not all crowded over there. Okay, 2 times 2, that gives us 4. 2 times negative square root 3 gives us negative 2 square roots of 3. Positive root 3 times positive 2 gives us positive 2 root 3. And then positive square root of 3 times negative square root of 3 gives us negative square root of 3, right? But we have 2 of them. Okay, so we can write this as negative square root of 3 squared. And remember that the square of a square root is just the number on the inside by itself. I'm just bringing everything else down. And so this will become a 3, right? Okay. And notice how the terms in the middle, they're the same. It's a negative 2 square root 3 and a positive 2 square root 3. They're the same, but they just have different signs. So these middle terms will always become 0 when you use the conjugate. It's always going to be 0. Okay? That's just a pattern. And so, well, what do we have left? We just have 4 minus 3, which becomes 1. So on the bottom, once we multiply by this, notice now that there are no radicals. All we have is a regular 1. And so you might not get 1 every time, but you're just going to get a regular number. You're not going to get a radical on the bottom anymore. And so now all we have to do is just multiply the top by the conjugate that we did as well. And the only reason we're doing that is because if we multiply something to the bottom of a fraction, we need to multiply the top by the same thing, right? So, okay, let's do this. 5 times 2 is 10. 5 times negative root 3 is just 5 root 3, and there's no simpler way to write that. So this is our numerator, right? We have 10 minus 5 square root 3 on top. And what did we have on bottom? Just a 1, right? But any fraction over 1 is just, like, we don't need the fraction, right? Any fraction over 1 is just itself. And so there's our solution for this problem. So the conjugate is a very powerful idea, and what ends up happening is always that when you have the same terms with just different signs being multiplied to each other, a times a squared, a times b, both positive, is positive ab. B times a, but negative b, only one of them negative, you get minus ab. And then b times b is b squared, right? But negative, because one of them is negative. And so you're always going to see this pattern where the middle terms become 0, right? And so you're always going to get a squared minus b squared. So when you multiply by the conjugate, essentially all you need to do is square the first term minus square the second term. And this pattern here is called the difference of squares. Okay, and where does that name come from? Well, if we're talking about a square, right, to find the area of a square is the same to find the area of a rectangle, which is length times width, right? Area is equal to length times width. And so a square is a very special rectangle. It just has all the same sides. So the length and the width are the same. In this case, they're a. A times a is a squared. This is a square too. B times b, b squared. And another word for subtraction is difference. So that's where the name comes from, difference of squares. So when you multiply by the conjugate, you're always going to get a difference of squares. Okay? And we'll cut the video here. See you guys next time.